Humans have been using technology to explore beyond Earth orbit since 1958. In fact, more than 250 robotic spacecraft, as well as 24 humans, have now ventured into space past near-Earth orbit. There are currently or have been spacecraft exploring Venus, Mars, asteroids Jupiter, Saturn, and the Kuiper Belt, as well as interstellar space. Most of these missions have since ended. However, we shall examine a handful of some of the most important ongoing and planned endeavours. It only seems appropriate to begin with NASA's longest-running mission ever. Voyager 2 was launched back in 1977 and has been exploring our outer solar system and beyond ever since. However, though launched after, Voyager 1 soon passed it due to its speed, making it currently the farthest man-made object from Earth, leaving our solar system back in 2013, travelling at 38,000 miles an hour and currently 11.7 billion miles from Earth. A huge number of space probes have been used to examine the planets in our solar system, and a number of asteroids ever since the start of our journey into exploring space, most notably including Saturn's Cassini, Pluto's New Horizons, and Jupiter's Juno. However, the vast majority of which have since ended due to reasons including fuel deficiency and those that are burnt up in their planet's atmospheres. Along with space probes, space telescopes have been used to explore our universe. With the planet-hunting telescope Kepler running out of fuel in September, NASA launched its most powerful planet-hunting telescope to date back in April, using the transit method in an area 400 times larger than that covered by the Kepler mission, TESS. In July, the Transiting Exoplanet Survey satellite slipped into an orbit between Earth and the Moon. The telescope is now starting to scan 85% of the night sky, stare down distant solar systems, and hunt for Earth-like planets. The 2-year observation of about 200,000 stars may potentially reveal thousands of new planets within about 200 light-years of Earth. So how do we power these spacecrafts? How do we communicate with them? And for those more ambitious manned missions in the foreseeable future, how can we keep people alive and healthy in space for such extended periods of time?
With regard to engine types, a lot has stayed the same since the 1959 moon landing. However, new plans are being developed that they'll be able to take space travel to the next level, allowing astronauts and satellites to go further than ever before. This section will discuss the present and future propulsion types used on spacecraft and their application within the aerospace industry. Chemical rockets work on the principle of conservation of momentum. A combustion reaction takes place within the reactor, which produces a large amount of heat. This heat is transferred to the combustion product, which passes through a throat, causing an acceleration, according to Newton's third law and the Bernoulli's principle. This heat can either be used to power the rocket directly in a chemical rocket, or can use heat produced from electrical resistance in a thermoelectric rocket. The fuel used can either be in liquid or solid form. Sometimes a hybrid is used. In solid form, the fuel and the oxidizer have already been mixed. These are the classic-looking fuel tanks which produce a thick white smoke on takeoff. They burn nearly 4,000 kilograms of propellant each second and produce a thrust of 12.5 meganewtons. Liquid fuel types use a combination of a liquid hydrogen, or kerosene, with liquid oxygen, which is sprayed into a combustion chamber through injection nozzles. There are two types, bipropellant and monopropellant. Bipropellant being the most common, where two propellants mix together in a combustion chamber. Monopropellant is where one unstable propellant decomposes when in the right environment and when supplied with a suitable catalyst. The benefit of using liquid over solid is that the amount of thrust can be controlled by limiting the amount of fuel that is sprayed in. Solid fuel burns uncontrollably. The problem with chemical rockets is they are fundamentally limited by the amount of energy held in the chemical bonds. Electrically powered rockets use electrical energy to create superheated plasma, which is fired through a supersonic nozzle to generate thrust. This type of propulsion can be split up into two types, ion and plasma drives, and non-ion drives. The difference being that ion and plasma drives generate thrust by expelling matter, whereas non-ion drives only expel photons. These high-efficiency mechanisms have been used in Russian satellites since the 70s, however will not be used for anything other than orbiting application due to their low thrust. The Dawn space probe is an example of a current ion drive. It is currently in orbit around the dwarf planet Ceres, trying to learn more about the formation and makeup of early solar system. Molecules of unreactive fuels such as xenon are given a positive or negative charge and accelerated by an electric field. This produces a very low thrust, equivalent to the pressure exerted by a piece of paper on the hand. However, for long-range mission applications, it can deliver 10 times as much thrust per kilogram of fuel than in a chemical rocket. In the proposed method, solar sails use the concept that momentum-carrying photons caught in a sail can be used to pick up significant thrust. The engines don't need to carry any fuel because they rely on power from the sun, which gets caught in the sails and transfers its momentum to the spacecraft. The downside of this is that as the solar sail moves away from the sun, sunlight becomes feebler and the level of thrust decreases. Radioactive materials are used across the world to produce power by nuclear fission reactions. On the other hand, nuclear fusion reactors can be used on spacecraft to produce large amounts of thrust at high efficiencies, almost 100 times more efficient than the best chemical rocket. Nuclear fusion is the same process that occurs in the Sun, where the atomic nuclei of hydrogen atoms are fused together to produce helium in a powerful exothermic reaction. Harnessing this energy can be done in two ways: continuous fusion and pulsed fusion. In continuous fusion, fuel is superheated to hundreds of millions of degrees until fusion occurs. Pulsed fusion differs in that the fuels are separated until they are combined and detonated in a controlled environment. A pellet of two hydrogen isotopes surrounded by metal rings made of lithium are dropped into a combustion chamber, where a large magnetic field slams the metal rings closed around the pellet, compressing the fuel to incredible pressures, leading to fusion. A grain of sand of this fusion material would have the same energy content as 4 litres of rocket fuel.
Sound cannot travel through the vacuum of space, but light and other electromagnetic radiation can, for example radio waves. Astronauts have devices in their helmets which transfer the sound waves from their voices into these radio waves, and these are then transmitted to the ground or to other astronauts in space, exactly the same as how a home radio works. The first ever communication from space was from the Sputnik 1 satellite in October 1957. It was the first satellite to orbit the Earth, and it broadcast out a simple radio signal that was able to be picked up on the ground by amateur radio operators. Currently, NASA and Roscosmos have virtually 100% communications contact with orbiting astronauts thanks to the Tracking and Data Relay System. This system is a constellation of 7 geosynchronous satellites, and it works with ground systems that act as relays between them. All of these facilities form the space network. However, launching all of these satellites took a number of years, and an additional 6 satellites have been launched with new technologies as part of system upgrades. Voyager 1 is currently a deep space probe which has left the solar system. It is 19.5 billion kilometers away. If a 20 kilowatt signal was transmitted from Earth towards Voyager 38 hours ago, 19 hours ago the signal was received, and a signal was broadcast by Voyager at a signal strength of 20 watts. This signal is currently being decoded by a deep space network station in Madrid at a signal strength of 9 times 10 to the minus 23 kilowatts. This is 1,000 times weaker than the signal a very good FM radio can receive. The total communication time between Earth and Voyager is 38 hours. The Deep Space Network consists of 3 antenna complexes stationed around the globe approximately 120 degrees apart: Canberra, Australia, Madrid, Spain, and Goldstone, California. The global separation of the stations allows most spacecraft to have an uninterrupted line of sight with at least one station regardless of the time of day. A listening station will rise before the last visible one sets. Voyager 1 is still visible from all 3 stations, however Voyager 2 is only visible from the Canberra site. Mars is 35 million to 140 million miles away from Earth, depending on the orbit of both planets. This means sending communication in a straight line between the two is not always possible. As communication travels at the speed of light, it can take between 3 and 22 minutes in delay due to this huge distance. The communications network currently in place for communicating with the Red Planet is the Deep Space Network. This is currently used to communicate with the rover missions on Mars, and this method could be used to communicate with future colonies. The way that the Deep Space Network works is that the rover transmits data to an orbiter which is orbiting the Red Planet. There is an 8-minute window per Martian day to communicate with this orbiter, and in this time 60 megabytes of data can be transmitted. The orbiters, then with their huge radio antenna and added solar energy due to the solar panels in orbit, can transmit this data back to Earth at a much faster rate. Looking ahead to interstellar communication. Using current technology, if there was to be a colony on Alpha Centauri, the closest star to our Sun, located here, the transmission delay in a message sent from the colony to Earth would be 4 years. This is due to the huge 40 trillion kilometre distance between them. To put this into perspective, Voyager 1 is 19.5 billion kilometres from Earth, and this is only a 19-hour delay. To tackle this, NASA is working on the Deep Space Optical Communications Project. This is a project by the Jet Propulsion Laboratory, which includes the use of laser light to transmit data. The light is in the near-infrared spectrum and as such has a much shorter wavelength than radio waves. This yields a data transmission rate of 10 to 100 times more than currently possible. Other ideas for longer distance communication include an interplanetary network of satellites which orbit not only the Sun but also the planets in our solar system and bounce messages back from spacecraft and colonies to Earth. This idea is very expensive and only suitable for radio waves.
There are many problems associated with maintaining life on board spacecraft far away from Earth. The explorers must overcome many challenges if they are going to see the furthest reaches of our solar system. Long-term space missions create tests of psychological endurance as well as many physical challenges too. The Mars 500 experiment was created to test the limits of human resilience by simulating the isolation of long space journeys by placing 6 men in a controlled test bunker for 18 months. By doing this, they concluded that the long-term isolation for space missions to Mars and beyond is achievable, although real missions will of course be more difficult. There are some real problems that zero gravity create for the human body. It stretches out the spine, and so astronauts can grow up to 3% taller in space. It can turn your muscles to jelly due to the fact the muscles do not have to work much in a weightless environment, which is why exercise is so important on long-haul space missions. Astronauts can lose around 1% of their bone density every month they spend in space, meaning that the bones are more likely to break when back on Earth. There are also many more problems humans face, such as vision and immune system problems, and it can be very hard to sleep in zero gravity. There are several theoretical ways that artificial gravity could be achieved which would eliminate entirely the serious effects of weightlessness. One way of doing this would be to have a rotating spaceship like the ones shown here. The floor would be the inside wall of the outer radius. The astronauts would feel a force pushing them away from the centre of rotation, which is equivalent to gravity to them. However, creating this is a real challenge as the spacecraft would need a source of energy to get it rotating, and if there is friction involved, then this energy will be needed to keep constant to overcome the force of friction. Also, due to the Coriolis effect, which states that any objects that move will have an apparent motion opposite to the direction of the spin, the spacecraft will have to be limited to a maximum of 2 revolutions per minute, but by doing this, it will also have to be very large with a radius of around 900 meters. There are 2 big problems astronauts face that cannot be overcome with artificial gravity. The first of these is sustenance in space. For all long missions, NASA does calculations that work out how much food is needed. An example of this is that a 3-year trip with a crew of 4 people eating 3 meals a day will need to carry more than 10,500 kilograms of food with them. As well as this, not getting the right nutrients is a real problem. Vitamin D is needed to be added to foods as the astronauts are not exposed to sunlight. The second of these big problems is space radiation. Even on the space station, astronauts receive over 10 times the radiation than what you'd get from being on Earth, because Earth's magnetic field and atmosphere protect us from this. There are many different forms of space radiation, such as galactic cosmic rays, and this chart shows the increased levels of radiation that come with interplanetary exploration. Long-term consequences of having increased exposure include having a heightened risk of getting cancer, as well as damage to the central nervous system, whereas short-term consequences include nausea, vomiting and fatigue. To overcome this, the long-haul spacecraft have to have shielding to protect the astronauts and monitoring equipment to the levels of radiation they're being exposed to. There is currently lots of research going into optimizing the shielding on spacecraft to help protect those astronauts on a journey to Mars and beyond.
Looking into future planned missions, the James Webb Space Telescope is scheduled for launch in 2021, and the attached telescope will show the best view of the cosmos ever recorded. It will feature 18 4-foot wide gold-coated beryllium mirrors and an enormous sun shield that will keep the apparatus from overheating. Once launched, it will provide images of distant stars that will teach us about the history of our universe, all the way back to the Big Bang, giving us an insight into how our solar system formed and the formation of other systems that could support Earth-like planets. It will take 30 days to fly 1 million miles to its permanent home, a Lagrange point, or a gravitationally stable location in space. Looking even further into the unforeseen future, a human mission to Mars has been the subject of science fiction, aerospace engineering and scientific proposals since the 19th century, and one which is currently very undetermined. In 2018, the race for a successful mission to Mars is officially on, with different organisations and countries each having their own Mars agenda, with 2 teams in particular sat in the top spot, SpaceX and NASA, both with undetermined projection plans still yet very far up in the air. With decade-long projection plans and billions of dollars of funding in question, it's anyone's guess who will be the first to make history. It could even be a company that doesn't even exist yet. With the human mission to Mars being as ambitious as it is, any plans for us to go beyond this propose challenges that we are not even close to solving. Technical limitations, with propulsion technology not yet advanced enough for such long distance travel, and of course human limitations, the time it would take to travel distances so far from our home planet, us as a species would face serious psychological as well as physiological issues. It's just a matter of time and space before we get there.